Nope. It's any set of x, y things put together. Relation doesn't have to have a rhyme or reason. Things can repeat. We don't care about that. A function is a specific relation, and a function says every x is assigned one and only one y value. Hence, when you do a vertical line test, every x has to hit only one y value. If it has more than one y value, it fails a vertical line test, and it's not a function. So technically, in a function, every x has one and only one y. Okay. We look at, God bless you, we look at the set of x values as the domain. We look at the set of y values as the range. And we determine if it's a function. Again, we're going to do a lot with domains and ranges, mostly domains. Some of you are still struggling with the domains when you have an exception to your domain. We use all real numbers. We have to remove anything that doesn't work for our real numbers. So, especially like on a test, if you had a fraction, so you can have a denominator of 0, and you found that x can't be equal to 1, you have to remove it from your allowable domain. So where your domain would have been all real numbers, your domain, all real numbers, if you can't use a value of 1, you have to remove this. So your domain then becomes, and always read left to right. Some of you had the sections mixed up. Continue left to right. Negative infinity, stop at 1. Now the reason we use a soft bracket is because we can't use 1. We can use 0.9999999, but we can't use 1. If we jump over it, we can use 1.000001, but we can't use 1. So we jump over it, soft bracket, to infinity. These are the domains we're looking for. We work on an all real number system, except for that one little time we throw in complex numbers for the quadratic. Everything else says real numbers. So if there's something that cannot be used, remove it. And this is what's left, your domain. So we start with the basic function. This, if you graph this, will become a nice little parabola. Is this a function? Because by looking at it, it passes a vertical line test, right? Is it a one-to-one function? No, because it fails what? A horizontal line test. So therefore we know that any set that we have where the x's do not repeat, any relation we have between two numbers where the x's do not repeat would give us a function. If we look at a one-to-one and you fail a horizontal test, that means your y's are going to repeat. So we can look at those y's and say they don't repeat, that's going to give us a one-to-one. Now there's a difference between a discrete set and a continuous set. This right here is discrete. There's a certain number of points in this, and that's it. If I graph these points, it would be 1, 2, 2, 3, 3, 5, 4, 9. I don't get to connect those points. There's nothing in between. They're discrete points, a finite set of points. Give me 4 points, plot them. If I graph this is continuous because I put my pen down. No matter what I graph here, I graph all these little points from my calculator, right? And then I connect them all with a continuous line. Everything exists between 2 points that way. It's a continuous function. I put my pen down and I draw my function. And you know to end your things with arrows, right? The regions also for Common Core is real fussy about those arrows, so I know you guys used a lot of those. Sometimes the kids would forget to do that, and on the old regions, they didn't really get as fussy, but Common Core says arrows, and they continue on and on. So we can look at our domain. Another way to look at your domain is look in your calculator. If x has any error next to it, you have a domain restriction. Something you can't use in your calculator says, oh, can't use it. Take it out of your allowable domain. Always start with your real numbers and remove whatever you cannot use. Okay, today's just like an overview of functions, just so that we all are on the same page. So which of these equations represents y as a function of x? So we're going to take this and we're going to solve in terms of y, and we're going to make sure that every x value has one and only one y. So if we solve this in terms of y, I'm going to subtract the x squared. I'm going to divide everybody by 2. If I plug an x value in, will I ever get 2 different y values for it? For one x value. If I plug a 1 in, it gives me a y. If I plug a negative 1, God bless you, it gives me the same y, but that's okay, right? Because that x value still only has one y. I'm only looking for a function. So every value that I put in, I will get one unique y. What is this going to look like if I graph this? Think back to your transformations. It's going to look like a parabola, and it's going to turn, like Gabby said, upside down because of this negative. So again, does that pass the vertical line test? Mm-hmm. Absolutely. So this guy is a function. This one will solve for y. And we'll divide by 2. And then what do I have to do to get y by itself? Square root. Now when you physically take the square root, you get a plus or a minus. So whatever this answer comes out, say it comes out to be 2. I get a plus 2, I get a minus 2. That's assigned to the same x. So is that a function? Mm-mm. And did you guys do y squares last year? No? That open up this way? No. Okay. So anytime you see a y squared, that's going to give you a sideways parabola. And again, that fails a vertical line test. But we can tell because if we solve this for y, as soon as you do this, you plug in one x value over here, and it's going to come out and give you 2 different y values. You have a plus or minus. Here's a rule of thumb. Whenever you physically undo the square, you always get a plus or minus. If your radical is there, if it looks like this to start with, then your problem, you only get the positive because you didn't undo this square. So in this case, it only comes out to be positive 2. So remember that. If you physically undo your square, 2 roots. If it's already there, it's whatever the sign is out there. And sometimes they put the negative right in front of this. Then it becomes negative 2. And I only still get 1 root. But when you physically undo your square, 2 roots. So this is telling me, nope, by definition, my x value will have 2 different y's. This guy is not a function. Not a function. And we actually do a lot more with your sideways parabolas in there. We do a lot more with them. And again, you can graph them in your calculator. Once you get them into y equals, you can look to see that your function passes your vertical line test. This is what we care about for a function. If it passes a horizontal line test, then it is a one-to-one. What does a one-to-one mean? Okay. What does a one-to-one function mean? Why do we look to see if it passes a horizontal line test? Because why? And that is true. We want to see that the y's don't repeat. What are we testing for when we do that? Good, to see if the inverse is a function. Very good. Because when we take an inverse, and this will start coming back to you. An inverse says you take your x, y, and you interchange them. That's why when we do the horizontal line test, it kind of flips them around. So to take the inverse of anything, say such as this guy, we would just flip these guys around. Which is why we cheated before and we said, did any y's repeat? Because now we can see, yeah, that passes the vertical line test, which means my original one was a one-to-one function. It passed the horizontal line test. So we're going to do a lot more with these guys. And what else? All right. Again, your domain is your x values. Make sure you start getting that hang of that domain. That's important. Okay. All right, let's take a look at a couple more things. What's this going to give me when I graph this? A V. Good. This is your absolute value. It gives me a V. Good. This tells me whatever x you put in here, the positive always comes out. So y is going to have to only be positives, right? And I need to test for the 0. What's the absolute value of 0? 0. So if you think about this, and I want you to start thinking about this, the 0 says, okay, I only have one sign for this. If I put in a positive 1, I get a 1. If I put in a negative 1, I get a 1. So there's a little reflection going on here. Is this a function? Is it a one-to-one? No. So this is a function. So what's my domain? All real numbers. And what's my range? 0 to infinity. What kind of bracket does the 0 get? A hard bracket, because I can use 0, right? Infinities always get soft brackets because it says whatever infinity is, you can always go one more. So there's no end there. So it keeps on going. So we give infinities a soft bracket. Hard brackets and soft brackets are really, really important when it comes to stating your domains. Now, this next guy, this is also an absolute value. This tells me the opposite is true here. So if I give you a value of x, let me put some down. Just a couple of values. If I give you a value of x, what if x is 1, what is y? Oh, 1 or negative 1, right? It could be 1 or negative 1, because this is the absolute value on this side now. If I give you a value of negative 1, what is y? Can't be, right? If I give you a value of 2, what is y? 2 or negative 2. And again, an absolute value can't be negative, right? How about 0? 0. So it looks like we have this. 0, 0. We have 1, 1. We have 1, negative 1. We have 2, 2. We have 2, negative 2. It goes this way. See it? Kind of like your sideways parabola. Didn't we say before? When the y squared is, it's going to go like sideways. So it's kind of like whenever you use the y part, it's going to come out sideways. So it's a little bit different way of thinking about that, but the same concept of an absolute value. Whatever comes out of here has to be positive, so that's not happening with my negatives. What's the domain for this guy? 0 to infinity. What's the range? All real numbers. Okay. What are these? Well, I'm sorry. Is this a function first? No. How are these two related? there are inverses of each other. Because look what happens. All your x values now become your y values. All your y values now become your x values. They're inverses of each other. Isn't it true? Isn't the inverse definition interchange the x and the y and then solve for y? Mm-hmm. So it's kind of like that. We can see that they're kind of inverses of each other. And this guy is not a function. You're going to see the same thing with your parabolas. They're going to work the same way. Now, function notation. Have you guys done a lot with function notation? Okay. Yes? Everybody good with function notation? Okay, so if I see f when x is 3, we say f at 3. If you say f of 3, that's fine. F at 3, f at x. This is where your x is. I tend to say of, because then I talk too fast and it comes out weird. So I tend to say f of 3. You can say at or of, whatever one works for you. You're going to say, okay, plug this into here just so that we hit 1 so that we make sure we're all on the same page. And then you solve. You can also put this in your y equals and look to see where is that in your table. That's another thing. Is this a function, this guy? It will give you what? A line, right? Is this a function, g and h? Good. So we're all okay with doing that? Are we okay with compositions? Okay, let's just take a composition in here and you tell me. Speak up if you're not comfortable. So I'm going to do this one. What do I do first? 2 into what? Good. Start at the right and always keep going to the left. So I'm going to take when x is 2, I'm going to go to my f and I'm going to put a 2 in here. This is the same as y equals. So 4 plus 4 is 8. What do I do with the 8? Put it into g. Good. So then I'm going to do g of 8. 8 squared minus 1. So my composition is equal to 63. Now they can put the little circle here, or they can just do it with parentheses. You don't have to put a little circle there. If we have more than one, more than 2 of them, same rule applies. Start at the right, plug this into H, plug that result into F, plug that result into G. Good? Okay, what about these down here? What if I do this? What am I looking to get? Plug it to, I'm looking to get one equation, right? Yes. So I plug in g of x into f. Okay, since we did this one with the f, I'm going to do this one instead, if that's okay with you guys, because we did this one. So we're going to be able to check to see if we did everything okay. So we're going to take f, still start at the left, start at the right, go to the left. The easiest way to do this is write this one first. Take this whole thing and plug this into any x. If there was more than one x value, I would plug it into both of those x values. So you're going to, God bless you, you're going to plug this in and you're going to square it. And then minus 1. Don't forget, this is not b squared. This is 2x plus 4 times 2x plus 4. And then I'm going to subtract 1. God bless you. So 4x squared plus 8 is 16, plus 16 minus 1. Now, to test it, we can take this 2, since we found that equation, and excuse me, plug this 2 in here. So this becomes 4, 16, plus 32, plus 15, that's 31, and we get 63. And we make sure that it works. So everybody's okay with finding the equation as well as finding the numbers? Anybody not okay with it? We're good? The important part is make sure you start at the right and you're constantly going to the left. Okay. Now the last thing is your difference quotient. Did you guys do this last year? Did the Miss Imperialis group do it? No? Okay. This is how a difference quotient works. This is your x, right? F at x. This is your x. Start like this. This is what we're I'm sorry. I'm stuck in my throat today. It's going to look like this. Eventually, it's going to look like this. So, this is the easiest way to start. This is an x, this is an x. Come back to this function. Map out your x's. Now, you're going to start writing this function when x is 2 plus h. So we're going to rewrite this function when x is 2 plus h. Oops, this has no square. Okay. We're going to start just replacing the x, kind of like we did with the function notation. We're going to replace it with 2 plus h. Then we're going to say minus, and we're going to put a parenthesis here, because it's going to be this entire function when x is 2. 3, we're going to plug a 2 in, because that's where x belongs. Okay. Now it looks pretty bad, but there's our goal. This is a problem with our domain. H cannot be 0. So it just kind of tells us h cannot be 0. You can find anything for h, but you cannot use 0. Our goal, therefore, is to eliminate h. Now here's the bad part. We work on this now, but it's not until the end of the course that you actually see why we do this. We use this in calculus a lot. And we use this for a few other things. We use the difference quotient. So when we get to the end and we do this little we do a limits unit for calculus so that we kind of know what's coming down the pipe for the next year, you'll actually see why this works. As h approaches 0, what is this going to be? But for now, our goal is to get this reduced so that we can eliminate h. Because h cannot be 0, so h is going to give us a problem in that denominator. So our goal right now is just to substitute these things in, work them out, and hopefully that denominator will be canceled out. Another thing, you cannot cancel terms, ever. You can factor and take out your factors. So you can't cancel h's at random. You have to make sure they all cancel out. So we're just going to work this out. We're going to distribute this. Be careful of this, because this says 2 plus h times 2 plus h and minus this whole thing. So be careful where your minus signs go. So 4 plus 2h plus 2h. So we're minusing this whole thing. With a subtract outside, distribute a negative 1, take the opposite signs, whichever one you like to call it. Whoops, I wrote the wrong thing. This is a negative. This was a positive over here. Sorry about that. Okay, so now, continue writing. And be careful of this. This you can actually put together. You can throw that in your calculator. 6 minus 4 plus 5 gives us a 7. So minus 7. Let's collect all your like terms and put them in descending order. We're almost there. got a negative h squared. I got a 3h and a negative 4h. What does that give me? Negative h. We have a 6 minus a 4 gives me a 2, plus a 5 gives me a 7, minus a 7, 0. If that didn't come out to 0, we would have a problem. Because our goal is to eliminate the h, which means we have to factor an h out in order to reduce that factor out. So now, I'm not going to cross out my h's. I'm going to factor out an h. Now I can factor out my h, and I'm left with that as my answer. Remember, our goal right now is to eliminate the denominator. That's all we need to concentrate on. We're eliminating the h out of the denominator. So we're doing a function notation. This is still considered function notation. When you did this before, you went into your function and you plugged in a 2. Didn't you do this before? Right? So now if I change this and I say 2 plus h, you come back in here, you're going to do the same thing. 3, 2 plus h minus 2 plus h squared plus 5. Isn't that what we have right here? So all we're doing is a little series of function notation. It just looks a little strange. Normally you're going to see it with the x plus h and the x. But this one had some numbers in it because you can do numbers and variables. You can put whatever it is you like in there. And then we did this again because now we said, oh, we have your function f. That's how we named our function f. We have your function f with a function notation with a 2. So we did this part and we replaced x with 2. I find the easiest way, and I still do this, I always put an x up here, and I always put an x up here. And I always put parentheses around my x's. It reminds me to change both of those. Because if I only change one, I'm in trouble. If you get down to this point, and you can't factor an h out of every term, that means something went wrong. Generally, I got to tell you, generally it's this minus sign somewhere. Because if you FOILed this but forgot to distribute your minus sign to every term, then somewhere along the line, I might not be able to factor out an h. Something's not going to reduce. Same thing that happens with the x's. If it had an x in there, your x's are going to have to cancel out by the time you're done. So our goal is to eliminate the h. That's our goal right now. Questions? Okay. So I gave you a little bit of everything for homework.